In today's video, we're going to discuss chi-squared. Chi-squared is a way of testing whether data fit a particular function. And it's a useful test that allows us to evaluate our experimental data in the context of doing of various theories. So first off, let's understand what the letter chi looks like. Chi is a Greek letter. It looks like an X, but it's a little more curly, and we always compute the quantity chi-squared. Now, hopefully you have watched or you will watch the Khan Academy video on chi-squared. They do a really nice job in a particular test of chi-squared. The video introduces the concept of chi-squared, and the example they used was a quiz where there were 4 answers, and the chi-squared test was used to see if the results were consistent with random. So they did 100 trials, and they looked at how often the right answer was A, B, C, or D. And in the video, chi-squared was defined to be the sum of the result they got, number of A's and B's and C's and D's they got, versus minus the expected. So in the case they were doing, they did 100 tests, they expected 25 of each, and so they compared the number they got minus 25 squared divided by 25. And then at the end, they concluded that the number of degrees of freedom they had was 3, because there were 4 possible answers. But once you knew what 3 of the answers were, you could figure out how many of the 4th ones there were. So again, I would go and look at the video. But the one thing they did is so they did this test where they just did a thought experiment where they did 100 trials, and they measured the number of times they got A, which in this case they said was 20, and they expected 25. B, again, they expected was 25 and 20. C, they got 25, and D, they got 35. And they went through and they computed the quantity chi-squared, which was the sum of the difference between the number they got, in the first case 20, minus 25 squared, divided by 25. And then they did this for each of the 4 terms. And then they looked this up and asked the question, was this consistent with what they expected? And they set a minimum expectation, the probability that their p-value was greater than 0.05. Now we're going to do something a little bit more general than that. In this video, we're going to look at a form of chi-squared where the errors are not necessarily due to the counting statistics. We will show that the chi-squared test can be used to test if data are consistent with a certain hypothesis when, for example, they have their own error bars. So let's say we have some data, and we'll say we have some y data, yi, where the individual points. In this graph over here, we have 6 points. And so for each of those points, there's a specific uncertainty, which may or may not be the same, sigma I. So that is that this first point is y1 plus or minus sigma 1. So the sigma is the value from here to here on the graph. And for each of these points, we can ask the question in this test, is our data consistent with the value 6? So before we start, let's remember a little bit about what we learned about uncertainty. So we defined in an earlier video the idea of getting our uncertainty from taking a number of measurements and taking the standard deviation. So we could time something a number of times, or we could measure something a number of times, and then we computed this quantity sigma, which gave us an estimate of what our uncertainty was. And we could write down that our best estimate was the average answer we got plus or minus sigma. And we said that the sigma was distributed like a Gaussian. And so for a Gaussian distribution, what we know is that the data are distributed in such a way that 2/3 of the time you should fall within 1 standard deviation of the mean. And 1/3 of the time you should fall outside of 1 standard deviation. So 68% fall within plus or minus 1 sigma, 95% fall within plus or minus 2 sigma, but still 5% of the time you will fall outside of even 2 standard deviations. And this is a Gaussian. Now, let's take this and go back and look at what we used for chi-squared. So what we saw is that we would expect that 2/3 of the time our data would be within 1 standard deviation of the expected value if we fit the data. And remember, this means that 1/3 of the time we expect to not be within a standard deviation. A lot of times students are happy to have their data within 1 sigma, but are not happy when some of it's outside of 1 sigma. Remember, sometimes data will be outside of 1 sigma even if it's a good fit. So let's look at our plot and let's see if we can, and let's ask how many of these data are within 1 standard deviation and how many are not. So if we look at the ones marked in blue here, this first one is clearly within 1 standard deviation of 6. This one here is, we'll count in red, is not. So we have 1 in, 1 out. And blue, this one is within 1 standard deviation just, so that's number 2 in blue. This is within a standard deviation, it's right on 3. This is at 4, and here we have one here that is out. And so there are 2 here that are outside 1 standard deviation and 4 inside, which is exactly 2/3, which in this case is what we expect. So we say, well, that makes sense, but how do we quantify it further? Notice some of these are much further than 1 standard deviation away, and some of them are much less. So what we'd like to do is to compute how far each of these points is with respect to their uncertainty from the value we're trying to test. And like many things, we don't care about the sign of that, we'll just test the square of that quantity. So let's introduce the quantity chi-squared. It looks like a complicated formula, but it's not really, and you'll get used to using it. So what chi-squared says we do is we compute for each of the values, we compute the sum of the value we got minus the value we expected squared over sigma for that uncertainty squared. So in this case, we were doing this test to see if our data lines up along with 6. So we know what y expected is at 6. And you might expect that this quantity, y minus y expected over sigma I, is of order 1 for each of our points if we're about 1 standard deviation away. Because on the average, you'd expect that on the average data would be about plus or minus 1 sigma from the mean value, or the value that we're testing. So let's go through and look at my horrible handwriting, and we'll compute chi-squared. We can actually read it off the plot and compute chi-squared for this graph. So let's go over here and see this first point here. Notice this data is 0, 2, 4, 6, 8. So this first point here is 5. That's y1 is 5, and sigma 1 is 1, 2, 3. So it goes from 5 to 8, and that's sigma of 3. Here we have a value of 3, y2 equals 3, and sigma 2 equals 1. So it goes from 3 to 2 down here and 4 up there. We do the same for this one. We find a value of y equals 5, and again, sigma is 1. We get this one over here. We have y is equal to, y4 is equal to 6, right on the number, and the sigma is 2. And we do the same for here. Y5 is 3, sigma 5 is also 3, and here we have y6. The last point is at the value of 10, and the sigma is 2. So we write down our formula, which in the first case is 5 minus 6, that's right here, squared over 3 squared, because that's what sigma is. The next case we do a value of 3 minus 6 squared, and the sigma for that one is 1, and we do this for all of our points. And again, my messy handwriting, but when you add this all up, the first one you get 5 minus 6 is minus 1 squared over 3 squared, which is 9. The second term is 3 minus 6, which is minus 3 squared over 1 squared, which is 1. You do this for all of them, you add them up, and if you do this, you get 15.1. So chi-squared for this particular plot is 15.1. What does that tell us? Well, what you have to do is you have to ask the question, first off, how many degrees of freedom do we have? Now, what we're doing, each of these individual points here is a test of whether our theory has a value 6. So we could have made one measurement and asked, does it agree with 6? But we made 6 measurements and asked, does it agree with the y value of 6? Note, in the Khan Academy, we found the video that degrees of freedom were 1 less than the number of measurements because one of our measurements was constrained. Here, we're given 6 externally, so we have 6 individual degrees of freedom. So we have a chi-squared of 15.1 with 6 degrees of freedom. What do? Well, we can look it up in a table. So let's go back to the original question. The original question was, is the data consistent with a theory that predicts a value for y equal to 6? So again, chi-squared is 15.1. We have 6 degrees of freedom. So we go over to the table here and we look up D is the degrees of freedom. We come down here and we see that 15.1 is pretty close to 0.01, but a little bit closer to a little bit on the 0.05 side. We might estimate that it's somewhere between these two, but closer to this one. So it's got a probability of 0.0, say 2. And that means there's a 2% chance, only a 2% chance, that if this data were in agreement with our theory, that we would get a chi-squared this large. So we can conclude that it's unlikely that our data are consistent with the theory because our p-value is less than about 2% chance. And if we set 5% as our standard expectation for agreement, then we can say that this is clearly not in agreement with our data. So chi-squared is very powerful in evaluating data. And what's kind of interesting is you can use chi-squared and actually look at a plot without even any numbers on it and ask the question, are the data consistent? So let's say, for example, on this plot to the right, we have a theory line, which is the line showed here, and we have 4 data points. And we ask the question, is this line consistent with these data points? So what we do is we want to compute. We remember that we get chi-squared by computing the value minus the expected for each point squared over sigma squared, or if you like, the value minus the expected over sigma, the whole thing squared. And you could rewrite this, if you like, as delta y, where delta y is the difference between the point and the value, over sigma I. So what this is saying is we can compute this quantity, which is the distance from the line in units of sigma. So what we want to do is this. So this says that chi-squared is the sum of how far each point is from the line in units of sigma. So we can actually then go and compute this just by looking at this graph. So what we want to do is we would like to look at this and see our plot. So if we look at this first point, we might estimate that this is about 0.2 of a standard deviation. It's about 1/5 of a standard deviation. So we write down here 0.2 squared, okay? And this is, if you look here, is 1 standard deviation, so we get 1 squared. And this one's just a little bit more than 1, let's say 1.1, so we get 1.1 squared. And this one is about half, because we start from here to go to here, so it's about 0.5 squared. So we can go through and actually do this individual thing, and what we get if we add the numbers up is we get a chi-squared of about 2.5. And here again, because we gave you the line externally, we have 4 degrees of freedom. So we can then take this and look it up in the table, and we say, okay, here's a slightly different table. This one has a slightly expanded table with both sided probabilities. But if we look here, 2.5 in our table with 4 degrees of freedom, all right, winds up somewhere between 0.75 and 0.5, because this is 2, 1.9, and this is 3.3, so 2.5 is right in the middle here. So we could say that there's about a 60% chance that you get a chi-squared of this value or larger, and that's a pretty good fit. So we say this data is completely consistent, and we've been able to calculate chi-squared just by estimating how far the point is away in units of the standard deviation and squaring it. Let's do this one more time. So here we have another plot, and we can estimate the same things. We can look and we can say this first one is about, let's say, a 1/10. So we take 0.1 squared, and this is about a quarter. This is about a quarter away from the line. So 0.25 squared, and this is the middle of this thing. So 0.05 squared, and this is a half, 0.5 squared. So we add up all these things, and we wind up with a chi-squared of 0.32 with 4 degrees of freedom. So we look this back up on our chart, and we say 0.032 falls very close to, for 4 degrees of freedom, it falls very close to this number, okay, which is 99%. So what this says is, if you did this experiment, 99% of the time, you would get a chi-squared this big or larger. meaning it's highly unlikely that you'll get a fit this good. You can say, well, what does it mean to have too good a fit? Well, what it says is too good a fit might mean, well, you're just very lucky, or it might mean that your errors are overestimated or incorrect. And oftentimes when we see something like this, the third possibility is that the errors are correlated with each other. But in this case, it's highly unlikely you would get something that fits the data this well with this large an error. So one final point to make is, in the Khan Academy video, chi-squared was defined to be the sum of the result minus the expected over the number expected. And we use instead the number minus the number expected over sigma squared. Why do they use n expected and we use sigma? Because they're doing a counting experiment. And for numbers greater than 5 or 10, sigma is the square root of the number. So sigma squared is the number. Many times in our labs, however, the errors are not due to counting errors. Clearly, if we measure a length to be 9 meters, the uncertainty is not the square root of 9. It wouldn't even be in a unit of meters. So the point is that for counting experiments, putting it over the square root of the number is fine. For a measurement where you know sigma, you put the individual sigmas in the system.